So we reached to this section here where we already calculated the deflection between the regions AB and BC. Now we need to get the maximum deflection because the question wants us to get the deflection to be limited to 1 millimeter. So in order to do that, we need to calculate the maximum deflection. So what is this maximum deflection? We have two regions. We have A to B and B to C. So we need to calculate the maximum deflection from A to B because there's an equation for A to B, and then we have to do the same for the region B to C. Right? So you can see right here in the video, in the screen, this is the equation for B to C. Now recall, in order to get the maximum or minimum of a curve, you find dy dx from calculus. But we already calculated dy dx. Dy dx is the slope. So from A to B, if you were to go, just scroll up, you would actually see that dy dx was this expression we had found. And we're saying that where this dy dx goes to 0 is the point at which we would have, or points at which we would have our maximum deflection. So we end up with this expression here. Now, how do we get x is equal? How do we solve for this when this expression is 0? How do we get the roots of this equation? So it's a bit difficult to do that by hand. So we'll use a tool called the WolframAlpha tool, and it's available on this website. Right, so what I'll do, I'll open it up here now. Right, so when you open the website, you would see it looking purple like this. This is the math input, meaning that if you want to be able to enter like these bigger equations. But we're looking at a straightforward equation. So we could go to natural language, just click on the tab there, and you could start entering the equation. Right, so for example, we could have minus 8.33. Right, so unlike MATLAB, where MATLAB you would have to put the asterisk for multiplication, here you can leave it as x. So there's no multiplication symbol. It already interprets it as multiplication. Right, to the power 3 plus 27.5 x to the power 2 minus 26.28, and this is equal to 0. So by putting this, Wolfram interprets this as you want to actually solve the equation. So this is the equation here. So this is to ensure that the equation was inputted correctly. And you can see this is the slope being plotted. So we have three roots, of course, because it's a cubic expression. And then you could get your 3 solutions. Right, so of course our region is between, for AB is between x is equal to 0 and x is equal to 3. So this is out. So we end up with these 2 expressions here. Right, so this falls within the region of x is 0 and x is 3. So how do we know where the maximum or the minimum is? We have 2 points that is valid. So for this now we could actually go ahead and plot the deflection if we want and determine now where the maximum lies or the minimum lies, because we have 2 points. So what we could do, we could open another Wolfram window, just remove this, and we could actually put in the deflection equation. So the deflection equation for y is between A and B is this expression here. So we could actually enter that, and we could say plot, right, because we want to plot a curve. Actually type out this equation. Okay, so if we want to plot that between x is equal to 0 and x is equal to 3. Hit enter. Right, so it's always important that you look at the input interpretation to ensure that Wolfram is working out what you want it to work out. So this is the equation from x is 0 to x is 3, and this is the curve here. Right, you could also plot it in Excel if you wish. And this way now you will actually see how the deflection would be. Right, you could ignore the y-axis values here because we have nothing calculated for E multiplied by I as it. Right, so we're just looking at the shape. So you could see this is where we have the actual 2.9. So we have a maxima here. And over here we have a minima. So if you look at where it lies, is actually between 1 point something. Right, so that would be the 1.23. Right, so we can see the minima of the deflection curve, or where we have the maximum deflection between the region occurs here at the 1.29. But sorry, 1.23. Right, so this will go back down in the notes here. Right, so this we have the equation we solve. Right, this is the plot. This actually is a sketch of the deflection plot here. Right, so we would say from the sketch we could see that x is equal to 1.24, where we have the maximum deflection. Substitute that, and we end up with, substitute x is 1.24, and we end up with minus 20 over EI. Now, if you already typed in the equation in Wolfram, there's no need to actually do out this equation. What you can actually do is, we have the equation entered already, so you could remove this bits here and say x is equal to 1.24, or you could go do the exact value, which is 1.236. Let's go with that. Let's take it 1.24, it's easier because this the remain with the notes. So you can actually evaluate it at a point. Right, so instead of you have to go in now and plug in x is equal to 1.24, you could actually do it like this in Wolfram, and it will give you the answer as minus 20, which is what we have here. Right, so you can see the answers are rounding off error again. So this is the maximum y between the region A to B. And we keep E and I as parameters that we do not know as yet. We know E is 200 gigapascals, but we leave it as E and I for short. The next bit is between the region of B and C. So we do the same again. We have the slope that was defined for B and between the region B and C. So that was the slope here. Right? We had calculated C4. C4 was 446.3. And then eventually we calculated C5, and we have the deflection between the region B to C. Right, so we're interested in the slope. We're saying the slope is equal to 0. So the max y occurs when dy dx equal to 0, and that's when the slope is equal to 0. And now we could again solve for x. Right, so we go through the same procedure as we did just now. So we could open a new window, and we could enter that equation into here. So we have entered the equation for the slope, made it equal to 0 because we want to find the maximum or minimum point, or the maximum or minimum point. Press enter, and this is what we get. Right, so the interpretation was correct, the input is correct here. So you can see the solutions or the roots are x is equal to 2.9 and x is equal to 5.05. Now remember that this equation is only valid for the region of B to C, which is between 3 and 4. And these 2 points here are outside of that range. So that means the maxima or the maximum deflection occurs mathematically outside the region. So we need to look for a maximum point then within the region. So what we could do, we could actually plot now the deflection formula if you want, and see this how it looks. And just read off from the graph what is the maximum value then. So that is what we will do now. Okay, so we want to plot the deflection between B and C. So we enter the equation here, we say plot just like we did before, and we type out the equation, and we want it between the value range which is 3 and 4. So this is the actual plot here. So you can see from 3 it actually just goes down, because remember we have that 60 Newton force pushing down on the end. So you can see down to the end here where x is equal to 4, which is the limit, we have the maximum deflection. So the maximum deflection between the region B to C occurs when x is equal to 4. So that is what I did here. So this is a sketch of the deflection, and we're saying at x is equal to 4, we have the maximum value of displacement. And again, now we could get that actual value by plugging x is equal to 4 into the equation. Again, there's no need to, if you type it out in Wolfram already, you could actually just put x is equal to 4. So we can evaluate the equation at x equal to 4. And we get minus 23.7. So that is your maximum displacement minus 23.7 over EI. So the larger maximum deflection occurs in the region BC. So this was between A and B, this was between B and C. So of course this one is the larger value. Remember again we're looking at the numerically larger value, not the fact that it's negative. Right? Because it pushes down in the negative direction of the y-axis, that's why we have the negative. But the actual value is 23.7 over EI. And the maximum allowable deflection in the question, in the beam, was 1 millimeter. So now we could actually make this value here equal to 0.001 meters. Right, so by solving, we end up with I is equal to 1.85, and you convert to inches. So this is the value in inches. Now we look to the table. So the table is what was given before the example. Now keep in mind that the value here is 0.285. So we could go up here. This is the actual table. So I'll zoom in. So we're looking at I, 0.0285. And you could see that somewhere here is where you would have your that value line. Right, so it cannot be 0.1, and that is too small. So it has to be the 0.3 value. Right, and that 0.3 value corresponds to 1.5 inches nominal diameter of this pipe. So it's an 1.5 inch pipe. Now keep in mind something that when we talk about pipe, if you were to measure the pipe around your house or something, like PVC pipe or something, even though it says 1.5 inches, the outside diameter is actually bigger. Right, so the outside diameter is actually 1.9 inches and not 1.5 inches. That and depends again on the schedule. The schedule has to do with the thickness. So the schedule 40 is a higher thickness than if it was schedule 20. So then this thickness would have been smaller if it was schedule 20. Right, so the outside diameter is 1.9 inches. The inside diameter is 1.6 inches. So now we could safely say that we have selected an 1.5 inch pipe for the application. It meets the requirement of a deflection of 1 millimeter, maximum deflection of 1 millimeter. Right, and the value of that I is 0.3099 inch to the power of 4, which we read off from the table. The next step is to get the maximum bending stress, and in order to do that, we need, of course, to get the maximum bending moment. Right, so between A and B, we have an equation, and we know that the maximum bending moment occurs where the shear force is equal to 0 or crosses the x-axis. So we make the shear force equal to 0, and we have the value for x. This is where the maximum bending moment occurs. We substitute it into the bending moment equation, which we calculated, and we get our 30.3 Newton meter. For BC, the maximum, well, the shear force is just minus 60. There's no equation in terms of x. So where is the maximum bending moment in this case? Well, for that, we could sketch out the shear force and bending moment diagram. Right, so this is why it's always important to always have at least these two diagrams for your beam. So you could see at this point here, when we start the region BC, it starts at one value and crosses the x-axis and continues. So where it crosses the x-axis, we say at this point here, where x is equal to 3, is where we would have our maximum bending moment. And if we sketch out our bending moment diagram, we could actually see it here. So at x equal to 3 is where we have our maximum bending moment between region B and C. Right, so this was the bending moment equation. For that region, we substitute x equal to 3, and we get the maximum bending moment as minus 60. So between the two here, 30.3 and minus 60, minus 60 is the larger of the two maximum bending moments. So we'll use the minus 60 to calculate our maximum bending stress. Right, so we have M is 60. This was the equation from bending stress. We have M is 60. Y would be the radius of the pipe to the outermost diameter. I, well, we need to convert I back into meter to the power 4 because this wasn't the I we calculated. This is the I from the table for the 1.5 inch pipe. So we convert it to meters. Right, again, we said Y is the radius, and we have the maximum outside diameter is 1.9 inches, so we divide that by 2, convert it to meters. So we have everything we need here to calculate the maximum bending stress, and then that will give us our maximum bending stress. And that is the problem, and the key to this problem really is using WolframAlpha as a tool to solve your complicated equations and that assists in getting the roots of an equation or substitute a value if you want a quick value. If you want to quickly visualize a plot, so it's nice for that, and it's free.